A modern AI has more knobs than there are stars in the galaxy. So, how does it know which way to turn even one of them? It turns out every model ever trained answers that with one question, asked over and over. One quick orientation. In case this is the first of these you have seen. This is season 2 calculus, and this episode is the one your textbook calls the derivative. You need nothing but school algebra to follow it, and everything else in the season is built on it. Before any of this, some history because it explains why the idea feels so strange the first time. The mathematics that trains every AI today was finished long before anyone had a machine to run it on. In 1847, Cauchy was solving systems of equations from astronomical observations, and he needed the lowest point of a function nobody could draw. No computer, no graph. Only one trick: measure the slope where you stand and step against it. That trick sat almost unused for a century until somebody needed to do it a million times at once, 300 years early. What was missing was never the mathematics. So the maths was ready. What is the actual question it answers? Think of a shower tap in a stranger's bathroom. You cannot read it. So you nudge it a little and feel what happens. Too cold. And you know both which way to turn and roughly how far. That is the whole method. First, what is being scored? 64 real data points, an input, and the answer we wanted. The model is one line with one knob, the slope. Right now the knob is set to 2. Every point misses by some amount. Those red gaps are the mistakes. Square them so misses in both directions. Count, average them, and you get one single number, 1.247. That is the score. Here is the smallest honest model there is. One weight, 64 data points, and a score that says how wrong it currently is. We are standing here. The knob is at 2 and the score is 1.247, and the model cannot see this curve. It only knows the one point it is standing on. So, which way do we turn the knob? Here is the trap in how this is usually drawn. We can see the whole curve, so the answer looks obvious. Just go to the bottom. The model sees none of it. It stands on one point in the dark and it has to decide which way to move, left or right. So try it. Nudge the knob by 0.1 and the score moves by minus 0.225. Divide one by the other and you get minus 2.25. That number is the answer to the question. Before I show you, take a guess. It makes the answer stick. We keep shrinking the nudge. Does the ratio keep changing forever, settle on one number, or collapse to 0? Now do it again with a smaller nudge, and smaller, and smaller. The score barely moves at all, but look at the ratio. It is locking in. 2.2, 2.36, 2.371. The digits stop moving one at a time and they settle on a single number, minus 2.37. That is how sensitive the score is to this one knob. One check before we name it, because a number that appears out of a shrinking nudge could just be rounding error. So compare it with what PyTorch computes directly. Same number, 6 decimals deep. What you watched converge is the real thing. And if any of these felt familiar, it should. Put a second point on the curve and join the two with a straight line. At school, that line has a name. It is a chord, and its steepness is rise over run. The run is how far along you moved, that is our nudge. The rise is how far up or down the curve went, that is how much the score changed. So here is the whole translation. What we call the nudge, your textbook calls the run. What we call the score moving is the rise. Our ratio is rise over run. And shrinking the nudge until the digits settle is what a textbook calls differentiating from first principles. Same thing, different words. Here is the same story as a picture. Put a second point a long way off and draw the line through both. As the second point slides in, that line pivots and it stops pivoting exactly when it touches the curve at one point. That final line, the one that just touches, is what the number means. Its steepness is the sensitivity. And the sign does the rest. Stand on the left and the sensitivity is negative, which means turn the knob up. Stand on the right and it is positive. Turn it down. Follow that instruction over and over and you walk downhill to the bottom, a weight of 2.999. The data was really made with a weight of 3. It found it. It has a name. This is the derivative. And every piece of it is something you already watched. H is the nudge. The top is how far the score moved. And the limit is the digits locking in. If the notation means nothing to you, ignore it. It is only a name for what you just saw. One warning. You will see it written dy by dx and it looks like a fraction you could split in half. It is not. It is a single number, the rate you measured. If you have ever trained anything, you have already run this. One line, lost dot backward. That line is doing exactly what you just watched for every weight at once. Every language model, every image generator, every recommendation feed, all of them are running this same question a trillion times over. So where does this actually sit inside a language model? A model like this has 3 modes. And here is the part that surprises people. When you are actually chatting with it, no derivatives are computed at all. Not one. We checked on the real GPT-2 during generation, 0 of its 148 weight tensors carry a derivative. Training is the opposite. Text goes in, runs through the layers, the model guesses the next token, and a loss says how wrong that guess was. And right there, at the loss, the derivatives begin. From there, one derivative is computed for every single number in the model. 45% of them live in the feed-forward layers, 32% in the embeddings, 23% in attention, 124 million derivatives, every single training step, all of them the same question you have been watching. Here is why this matters more than it looks. Suppose you did not have it. One knob, one score, and no way to measure a slope. All you can do is guess and check. To pin the knob down to 1000. A fine grid takes 5000 tries. Guessing at random takes about 2300. Using the slope takes 5 steps, and that is for one knob. With 2, the grid squares to 25 million. Real models have millions of knobs, which is a problem we will have to solve properly later in the season. It is worth knowing where this breaks, because it is a live research problem. If the score jumps instead of sliding, there is no slope to read. If the model has to choose a word rather than turn a dial, you cannot nudge that choice by 1000th. And if the thing you want to improve is somebody else's system, you get an answer and never a slope. Every one of those is somebody's research problem right now. Now, let us actually run it, because none of this is worth much if you cannot reproduce it yourself. 64 points, 1 weight, and the score at a knob of 2, 1.2469. 2 lines reproduce the whole thing. Shrink the nudge, and watch the digits stop moving. And now break it. If shrinking the nudge helps, surely smaller is always better. Watch. At 10 to the minus 16, the answer is exactly 0. The two scores were so close that subtracting them cancelled every digit the computer had. Nudging has a floor, and that is precisely why real frameworks do not use it. AutoGrad gets the same number with no nudging at all and no floor. That is the machinery every framework is built on. And 5 steps of following that number lands on 2.9991. The model found the weight the data was really made with. The whole notebook is in the description. Run it, change the numbers, break it yourself. So that is the question. If I nudge this number, does the score get better or worse? And by how much? Every model ever trained is that question, asked a trillion times. One knob is easy. Now do it with a billion of them at once, and that is the gradient. Thanks for watching and keep exploring. Next time, how AI finds downhill in a billion dimensions. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.